So we need energy conservation to get a get the value of Ts. Okay. So in order to calculate the surface temperature, energy conservation is required. Okay. Please understand, if a droplet, if you take a fuel droplet which is evaporating or burning, that is an indication for us boiling point. When it is burning, it is nothing wrong to assume the surface temperature to be very close to boiling point. So that assumption can be made, but here it is not possible to make a like assumed value for the Ts. So we have to again solve, because the Ts can be higher. So particle can be continuously heated and Ts can be higher also. So there is no restriction for Ts here. When a liquid droplet, there is a restriction that the droplet surface temperature cannot cross the at a steady equilibrium evaporation condition, the surface temperature cannot cross the boiling point. So here we have to use the energy conservation to arrive at the value of the Ts. So let us do energy balance. Energy balance let us try to do on a surface, at the carbon surface we will do this. So m dot C and its own enthalpy Hc. Similarly here m dot CO2 and HCO2, and here m dot O2 HO2. Okay. So this is the left hand side what I am trying to do here. So this mixes, so this and this added together subtracted to this. So this will be the so this will actually go to other side basically. So this is the chemical reaction, there will be heat released due to chemical reaction. This can be represented by m dot C into delta Hc, which actually we have demonstrated when we did the droplet combustion also. Now once there is a heat which is generated at the surface, because here everything is completely within the surface, there is no other reaction zone. So from the surface there will be a heat transfer. So this side, this is the surface RS, there will be a heat conduction from the surface to the interior. So S2I is the heat conduction from the surface to the interior of the carbon particle. Then there will be a heat conduction from the surface to the ambient. So this I will say QS to A and this will be QS to I. Okay. So now then there will be radiation of this radiation from the surface to the ambient surrounding temperature. So these are the two things, but in our analysis we have made an assumption that the Ts is constant. So in the surface there is no temperature gradient in the particle. So the heat conducted into the carbon can be taken as 0, because there is the carbon particle is assumed to be at a uniform temperature of Ts. Okay. Now QSA is the heat conducted from the surface. So we have to write a conduction equation for this. So minus Kg, Kg is the gas phase thermal conductivity. Okay. So this Ka dt by dr. So that is the so temperature decreases in the increasing radial direction. So negative sign comes for that, and the heat is also conducted away from the surface to the ambient. So this is positive quantity again. So now radiative heat transfer, grey body. So the carbon surface is assumed to be a grey body. So constant emissivity for the surface into the area of surface, Stefan Boltzmann constant sigma Ts power 4 minus T surrounding power 4. So this is the bulk radiative heat transfer. So this emissivity will not change with this. And also one more thing here is, it is not occurring in vacuum. So please understand there is a surface, so Rs, okay, and there is a surrounding, so R infinity let us take. So there are gases here, there are several gases present here, but we neglect the participating media here, these gases, which will actually affect the radiation, because in vacuum we can write such a statement, but if it is there are gases, then the gases also will absorb some heat, correct, but we neglect that. So in the it's a simplified model. So, we do not take into the account, only the grey body radiation is taken into account, where the emissivity is taken as constant, surface area sigma times Ts power 4 to T surrounding power 4, that is all. It is not affected by anything else. From the surface it radiates to the ambient, that is all. So, the gases, participating media affecting the radiation etc. is not taken into account here. So, this is simple energy balance I do here. So, this is the heat of reaction, delta H heat of combustion into the mass flow rate of carbon. So, this we know, this is another equation which is generated here. Now, somehow if I can substitute for the dT by dr at the surface, for which we need the profile. So, gas phase energy conservation equation we solve and try to get the T as a function of R, Tr profile, then I differentiate it with respect to R, dT by dr, and apply that to R equal to Rs, and I substitute here to get the value of this. So, that is the next thing, but we have already done that. Okay. So, to obtain the expression for the gas phase temperature gradient at the surface, that is dT by dr at Rs, we need to consider the energy balance within the gas phase. Okay. It is a simple one, second order equation which is solved, and by using appropriate boundary conditions we will get T as a function of R, and now we can differentiate this and put R equal to Rs. Okay, we have already done it, and whatever we have done for the droplet evaporation, okay, whatever we have done for the droplet evaporation problem, same conservation equation and same solution is applicable here. So, by taking the Z equal to Cpg by 4 pi kg and replacing T boil by T surface here, then we can write the differentiate the Tr solution which is got earlier, and put R equal to Rs, we get this value. So, Z m dot C by Rs square into T infinity by Ts exponent of minus Z m dot C by Rs divided by 1 minus exponent of minus Z m dot C by Rs. So, this will be the surface, the gradient of temperature at the particle surface. Now, this expression is plugged into this equation here, okay, and you get the you can write the carbon burning rate again, correct. So, again you can see that if you write the carbon burning rate with that, you get MC, and with as a function of Ts, again iteratively you have to solve it. So, that is the equation we get. So, m dot C, I just substitute that m dot C delta Hc, this equation delta Hc equal to, now I have substituted this dT by dr at Rs to this here, and I got this equation here. So, m dot C Cpg into some exponential terms into T infinity minus Ts plus the radiation term. So, this is what I get, and you can see that this equation will be iteratively solved because MC and Ts both are unknown here. So, when you want to solve for MC etc., again you have to use this. So, couple this equation plus this equation to solve for the mass burning rate of the carbon. So, that is the way we solve for the one. It is a simple model, one film model where we solve like this. Okay, now, the next is two film model. As I told you, in this predominantly CO2 and C reacts at the surface Rs to form CO, and the CO diffuses towards the flame which is at a particular radius, say RF, from the interior. Then you say the gas phase reaction between the O2 and CO occurs, and CO2 is formed there, producing a peak temperature at that location, thin flame sheet. This is a thin flame sheet. Okay, now the temperature diffuses towards the surface, say Tf and Ts. So, that is the profile here, and in the ambient it decays to the ambient temperature. So, this will be the T infinity here. So, now carbon dioxide goes to ambient as well as it reaches surface. So, this will be the CO2 at the surface, that value, okay, and this is this Y CO at surface. Okay. So, this is Ts what I put here. So, now goes to a low value here, CO2 goes to a low value. Oxygen from the YO2 infinity goes to a 0 value at the flame. So, at the thin flame both CO and O2 are assumed to be completely consumed, and this is the reaction. C plus CO2 occurs at this sheet, that is a carbon surface. So, CO2 reacts with the hot carbon particle surface as a surface reaction and produces CO, and the homogeneous reaction occurs at the and it is an infinitely fast reaction producing a thin flame sheet. So, this is the two film model. Why this model has been developed? Because when you measure something here near to the surface, there was actually very little oxygen or no oxygen at all measured here. So, that means that oxygen diffusion to a surface is not possible. So, that was one indication, and the CO2 was higher than CO. So, that is another indication that CO is predominantly formed at the surface. So, based upon that, this two film model was constituted, and again when you increase the complexity, your problem also will be more complex. We are not going to solve everything, but we will give the procedure to solve as well as the final equation. Okay. So, you can see that again like in the droplet combustion, there is the inner zone here where from the surface to the flame, that is the inner zone, where you can see that the CO2 formed diffuses towards surface, participates in the surface reaction, and CO forms there, and that diffuses towards the flame and gets consumed there. So, oxygen is not present here. So, if you see here, CO and CO2 are the two species what we have. Okay. Go to the ambient. Ambient you have this. Okay. One more thing is nitrogen also is present. Nitrogen will be everywhere. That is another complexity in this. When you use air, nitrogen will be there. Nitrogen will not be consumed here. So, nitrogen will be here and also here. So, due to the presence of nitrogen, you can see that there will be some oscillations for oxygen, CO, and nitrogen will be there. But nitrogen is inert, so it will not participate in any reaction, but it will be there in both the zones. Okay. So, if you do not consider nitrogen, the other species are only two species here. So, in the outer zone here, outer zone, you have O2 and CO2 and the inert species. So, I say this is inert species I. Okay. CO2, O2 and inert species. In the inner zone, CO, CO2 and inert species. These are the three species what we have in the zones. Okay. So, this is again what we have seen in the droplet combustion thing, but in the combustion there will be only one reaction zone which is at the flame, but here there is a reaction zone at the flame which is homogeneous in nature, gas phase, and there is a surface reaction at the surface. So, these are the two things which will differentiate between the particle combustion, carbon particle combustion and the droplet. Now, let us see the species flow rates. Species flow rates basically. So, now carbon surface, so RS, okay, m dot C, okay, CO is formed and that goes away like this, MCO. CO2 which is formed from the flame that comes in. So, I will say this is the mass flow rate of CO2 in the inner surface. I is the inner surface, represent the inner surface. So, this is the conservation here. Okay. So, that is the conservation of this. Okay. Now, I denotes the inner region, as I told, inner region between the surface, carbon surface and the flame. Now, from this you can write m dot CO will be equal to m dot CO2I plus m dot C. Okay. Now, what is happening at the surface is the surface reaction. So, this is the surface reaction here. 1 kg of carbon, S1 kg is, because there are two reactions, the stoichiometric coefficients are designated as S1 and S2 here. For the surface reaction, I am designating the stoichiometric coefficient as S1 kg of CO2, giving 1 plus S1 kg of CO. So, now mass balance m dot CO equal to m dot CO2 at the inner plus m dot C, which is written as 1 plus S1 times So this you know, no. So from this equation I can write 1 plus S1 times mass of C will be equal to that of CO2. So now I put this S1 times oxygen is S1 times MC. So CO2 is m dot of CO2 here, that is oxidizer here, will be equal to S1 times m dot of C. So when I put that, I get this equation 1 plus S1 times m dot of C. The mass rate of CO2 is written as S1 times m dot of C. Okay, this is I'll say I equal to S1 times m dot of C due to this plus MC. So 1 plus S1 times MC. So that we can write. So this you keep in mind. So this is the fluxes in the or the flow rates in the carbon surface. Now at the flame surface, and this is the flame here, flame RF, and this is RS. So now what happens to the flame? CO which is formed, that goes here. Okay. Now CO2 which is formed at the flame will come here like this, inner zone, and it also get away to the outer zone, m dot CO2 O, and oxygen from the ambient comes in here, so m dot O2. So these are the mass balances, correct, in the flame RF. So m dot CO minus m dot CO2, this is actually inner will be equal to, so m dot CO and this in the inner scene, this is going away, this is coming in. So that equal to m dot CO2 O which is going out, m dot O2 coming in. So this is the balance. Okay. So subscript O is the outer region between the flame and the ambient. So this is inner region and this is outer region. So now what is the reaction taking place at the flame zone? This is flame. What is the reaction? Gas phase. Okay. So 1 kg of CO, S2 kgs of O2 giving 1 plus S2 kgs of CO2. Okay. So now what we did there, we will do the same thing here. M of O2 will be equal to S2 times M of CO, or S2 into 1 plus S1 times M of C. Combining this we can write. So here also you can see that when we combine this, M CO2 outer will be equal to MC plus MO2. That is it. When I combine here, so you know this equation here. Okay. So MCO minus MCO2I, MCO minus MCO2I. Okay. This is MC. So this is substituted here as MC. So now I can write m dot CO2 equal to MC plus m dot O2, and I also use this equation to write every flow rate in terms of MC. So the main purpose of this is to write all the flow rates as the carbon flow rate from the surface. So I have already written for the CO flow rate of carbon using the surface reaction coefficient 1 plus S1 times m dot C. For O2 it is S2 into 1 plus S1 into m dot C. For CO2 going out, it will be 1 plus S2 into 1 plus S1 into m dot C. That is it. So when I do this, all the flow rate, so that this means that I need to only solve for one species CO2, that is enough for me. Then I can write everything in terms of this. So let us take CO2, and I can solve the CO2 in the inner region and outer region and formulate the problem. So I am not going to solve it. So the procedure for solving, the solution methodology is outlined here, which is as follows. Okay, the solution methodology is so there are basically I am interested in solving 5 unknowns. When I am mainly solving the burning rate of carbon, so that will additionally involve 4 more unknowns. First is the mass fractions of CO2 at the flame and at the carbon surface. Okay. So at the flame there will be a CO2 at the flame, at the surface RS we will have Y CO2 at S. So these are the 2 unknowns I additionally have. Similarly, mass fraction of nitrogen at the flame. Please understand, nitrogen is inert species. that will also penetrate everywhere. So, what is the value of nitrogen at the flame? Okay, y here in the flame again yn2 at the flame, I want this. So, these two I want, then the flame radius itself is unknown. So, if you, these are the 5 unknowns I want to solve, okay, basically. In order to just solve the basically primary variable is burning rate, that is what I am interested in. So, I will take CO transport in both inner and inner, which is between the carbon surface and the flame, and the outer, which is between the flame and the ambient. So, and appropriate boundary conditions will be used. Okay. What are the boundary conditions? You know that already we have discussed. So, at the surface YCO2 R equal to RS, YCO2 will be equal to YCO2S. At the flame YCO2 will be equal to YCO2 F. At the infinity it will be YCO2 infinity. So, using boundary conditions we can solve. Similarly, though that these are the boundary conditions, we can solve this. So, two equations will be got when you solve, one for inner zone, one for outer zone. When you solve this, CO2 transport is taken into account, we will take two equations. I want 5 equations. Then the second is transport equation, again nitrogen has to be solved. So, inert species, say nitrogen, I will get one more equation. So, here again we will consider the outer zone and try to solve the nitrogen. I will get one more equation for nitrogen. So, 3 equations are got now. At the flame sheet, oxygen is consumed, CO is consumed, only 2 species are there. What are they? The inert species and the CO2 which is formed. So, this identity applies, yn2 plus yCO2 equal to 1. So, I use this, that is the 4th equation I get. The 5th equation will be the kinetic equation. Okay. Let us take the kinetic equation at the particle surface, that will be the 5th equation. Okay. I am not going to details of that, you can refer the terms. Again there are also limited details are given, so you can check them. So, you can see that again some complexity is there, we have to form 5 equations and solve them. Finally, you get a expression like this for the mass burning rate of carbon, which is very similar to the droplet combustion, 4 pi Rs, okay, driving force rho d, natural logarithm of 1 plus a B number. Okay. The B number is written in different way. Okay. So, this is a B number here. So, I will say the B for carbon. Okay. So, now again you can see that there is an unknown here. For solving this, we need a surface temperature. The surface temperature is determined by again energy balance, which we have illustrated for the one film model. Similar energy balance you have to make both at the surface of the carbon particle as well as at the flame sheet to get the surface temperature. So, you have to solve this along with those energy balances, and iteratively you have to follow the procedures what are illustrated earlier to solve this. So, two film model, finally you will get profiles like this and a burning rate for this, which will be slightly accurate than this and than the one film model. So, these are this illustrate the methodology which is involved. Okay. But please understand that in reality any carbon combustion is not so easy. So, one film or two film model, it is much complicated. So, we need lot of assumptions to make, and like simplification what we have done here, such simplifications have to be made at any point in time. Okay. So, let us see one example on this. So, let us consider one film model and try to estimate the burning rate of a carbon particle which has a diameter of 250 microns. So, 250 micron carbon particle is burning in a oxygen environment, still air environment, stagnant air environment, and the particle surface temperature, the entire particle is at same temperature of 1800 Kelvin, and the mass fraction of the oxygen in the ambient, the standard air. So, 0.233 is the mass fraction. So, YO2 infinity is 0.233. Okay. Now, the kinetic rate constant Kc is given as 13.9 meter per second, as I told the unit is meter per second. So, now one more thing what is given is since the gas phase species are CO2, O2 and N2, we can take the average molecular weight or a mean molecular weight of the gases is equal to 30 kilogram per kilomole, and mass diffusivity has to be calculated at the temperature here, okay, 1800 surface temperature, because we are interested in surface reactions there. So that is equal to 1.57 into 10 power minus 4 meters square per second. We can also estimate this from tables. So these are the values. So this D, this is the value of D. Okay. Now how to calculate the mass burning rate of the carbon? So density is calculated from the ideal gas equation of state, rho equal to P by RT, but R is the R of the mixture. So mixture R is estimated by the RU by molecular weight. So that is got. So then if you substitute here, Ts is 1800 Kelvin, you get the rho as 0.2 kilogram per meter cube. That is the density of the gas mixture. Now density of the gas mixture is known, D is also known, so the product rho D can be calculated. Now this the reaction takes place at the surface, which is the heterogeneous reaction, 1 kg of carbon plus S kg of O2 giving 1 plus S kg of CO2. The S is stoichiometric air-fuel ratio is S, so S equal to 2.667 here. Okay. So we can get the value of S. Now I calculate the resistances. The diffusion resistance is nothing but S plus YO2S divided by rho D into 4 pi RS. So now as a first step, I will assume the mass fraction of the oxygen at the surface to be 0. Okay, 0, and calculate the resistance for the diffusion as 5.47 into 10 power 7 second per kg. This is what I get, second per kg. So rho is 0.2, diffusion coefficient is 1.57 into 10 power minus 4, which is given. So 4 pi into R, this R is, see the diameter is given as, so D by 2 and converted into meter. Okay, so D is 250 microns, so 125 is the 125 microns is radius, so 125 into 10 power minus 6 meters. So that is the radius here. So substitute it, I get the R value. It is 5.47 into 10 power 7. Now kinetic resistance is evaluated. In this you can see that S RU TS divided by 4 pi RS square, molecular weight of the mixture, rate coefficient and P. Okay, so go back one second. Yeah, I think this 2 is correct. So this 2 should remain there. So 2 is correct here. So if you go here, you can see that this pressure is 1 atmosphere. Substitute here. Kc value is 13.9 meter per second is given. Molecular weight of the mixture is 30, and RS square is 125 microns. So 4 pi RS square. So S is given. So if you substitute all this, you get this 4.81 in 10 power 6. The previous was 5.47 in 10 power 7. So you can see this resistance is 1 order of magnitude less, or 10 times, or diffuse 10 times more than approximately 10 times more than R kin. So this means that the combustion is diffusion controlled. But anyway, we will use the both resistance to calculate the mass burning rate of carbon as 0.233 is YO2 infinity divided by this plus this. I get the mass flow rate of carbon as 3.96 in 10 power minus 9. But I will try to verify now. I try to find the mass flow rate of carbon as YO2 just using the kinetic resistance. So this is R kin. Okay, so YO2 S divided by R kin. Now I try to estimate YO2 from this with the known value of MC now. Now I get YO2 S as the MC into R kin. So R kin is this into MC is this. So my substitute and multiply, I get YO2 S is very low value 0.019. Now we recalculate with this value of YO2 S the diffusion resistance, that is 5.45 into 10 power 7. Previously I got 5.47 into 10 power 7. So that is only a little change. So since the change is negligible, no more iteration is required. So we can just leave the burning rate as this. That's enough. So this completes the exercise, worked example.